Welcome back. It's 11, so I think maybe a few more people are coming in, but we're about ready to start. Okay, so welcome back to the to this session. We have 4 talks on defenses against side channel attacks, and the first talk today is from Wang, who will talk about mitigations for serverless applications. Go for it.
Hi. Thank you for the introduction. Today I'm going to talk about our ongoing work with my supervisor Aastha at the Systopia lab at the University of British Columbia. This work is about mitigating microarchitectural side channel for serverless applications. And I will tell you about what's the problem here, what's our insight, and what's our current solution. This is work in progress, so I'm happy to take any feedbacks and have further discussion. So let's start with the serverless architecture. Today, serverless platforms run serverless functions from different tenants on a shared server to achieve multi-tenancy. Even though serverless functions are from different tenants run in logically isolated compartments, for example, the virtual machine or Docker containers, they end up with sharing the hardware resources, including CPU, cache, RAM, etc. And the resources sharing in serverless leads to microarchitectural side channel. When one of the tenants become an adversary, the adversary can monitor the shared resources usage. And if the resources usage of the victim function is correlated with secrets, the adversary can infer the secrets of the victim according to its observation of the resources usage. But how does this observation like secrets? Let's assume that we have a serverless function whose source code is public, but all the user's input are secret. It takes my user secret, check my passport, and look up my salary with my social insurance number. However, I don't want to let anyone know my passport, nor my social insurance number. But meanwhile, we assume that the adversary have 2 types of observations. First, the program's execution time, and second, the cache access pattern, such that the adversary can carry out the corresponding timing side channel and cache side channel. First, by observing execution time, the adversary can infer if the branch is taken when it notices that the program takes a longer execution path as it has a longer execution time. Or the branch is not taken when the program has a shorter execution time, so that leaks the value of the condition. With cache side channels, the adversary can infer the value of the key in the array or map accesses. For example, using prime and probe attack, the adversary can first prime the cache with its own data and let the victim execute. After victim's execution, he will evict some data from the cache. Then the adversary can access its own data again to get a cache hits and misses pattern. Different keys and leads to different access hits and misses pattern, and it tells the adversary what key the victim is using. So in this case, that's my social insurance number. Well, in fact, more user secret can be leaked. Examples include personal identifiable information, login credentials, online purchase information. And to show the feasibility of such attacks in serverless environment, we are currently actively working on constructing the last level cache side channel attack on the V8 engine. Prior work proposed constant time to address this problem. Since the attack arises from the resources usage variability, previous researchers pointed out 3 source of variabilities. First, branches and indirect calls on secret value. Second, memory accesses with secret indexes. Third, variable time instructions with secret operands. At a high level, constant time execution requires eliminating all these variabilities in your program so that the execution of the program is regardless of the secret. There are 2 general approaches to achieve constant time execution. The first approach is to ask the developers to write constant time code and using verification tool to check if the handwritten constant time code is really constant time or not. The verification has various implementation. You can use empirical fast testing, type system, or symbolic execution. However, writing constant code is not easy, and also the compiler might not respect the source code level constant time property and violate it during optimization passes. The second approach is to use to generate constant time code automatically. This requires two phases to achieve end-to-end constant time execution. We first need to use transformation tools to convert non-constant time code to constant time code. Then we have to use preservation tool to compile the constant code into constant machine code. So far, most tools focus on cryptography libraries written in domain-specific languages or static type languages. But what about serverless applications? Well, due to the limitations addressed above, prior work is not applicable to serverless domain because, first, writing constant time code is difficult, even for cryptography library developers, and it will be extremely hard for serverless developers without security expertise. Second, DSL is not an appealing choice for them because serverless developers tend to use feature-rich languages like JavaScript and Python. Thus, these serverless languages have language runtime that may violate constant time property when interpreting the language bytecode or doing compilation and optimizations. So here we present our solution, Scooti. Scooti provides automatic microarchitectural side channel mitigations for serverless applications. We currently focus on applications written in JavaScript, which is the most popular language in serverless environments. At a high level, Scooti modifies the JavaScript V8 engine to automatically transform non-constant time JavaScript code into constant time JavaScript code and ensure its constant time execution at runtime. So this is the overview of our modified V8 workflow. After using the vanilla V8 component to parse the source code, the CT transformer will transform the regular bytecode into constant time CT bytecode. And the CT interpreter interprets CT bytecode while preserving CT property. The CT bytecode will also be translated to CT CF node, which is another intermediate representation in base. And CT compiler will take it and generate constant time machine code. In general, we add CT transformer, modify the original interpreter to CT interpreter, original compiler to CT compiler to generate constant code and preserve constant property during execution. In addition, we modify the V8 runtime to obfuscate the secret dependent memory access. And now I will quickly go through the technical challenges involving in implementing Scooti. This includes, first, language runtime can leak secrets, so we need mitigation there. And unlike transforming integers in cryptographic libraries, our transformation must be able to handle arbitrary data types. And third, hiding access pattern in complex data types becomes inefficient. And thus, our transformation is now at runtime, so we also want to minimize its runtime overhead. In this presentation, I will only focus on the first three challenges. So first, language runtime leak secrets. This is not a problem for prior work because they did transformation at LLVM IR level, and they assume that the compiler is trusted to get constant time machine code, and then the CPU can execute the machine code instruction in a constant time manner. Unfortunately, language runtime doesn't interpret bytecode instruction in a constant time manner. During bytecode interpretation and compilation, there are fast execution passes that use the value of the operand to improve the performance, but it doesn't ensure the CT constant time execution. So we also need to transform those bytecode handler to ensure the runtime constant time execution. We combine these three components to resolve this problem. We add CT transformer to transform the non-constant time V8 bytecode to CT bytecode. We have CT interpreter, which use transformed bytecode instruction handler to achieve constant time execution of the CT bytecode. We have CT compiler to compile the CT CF nodes and generate constant time machine code. The CT-CF node is directly translated from CT bytecode without changing the semantics, so it can preserve the CT property of CT bytecode. And since the bytecode we assume is public, transformation itself is also constant time. So our modification will be sound and complete because we achieve algorithmic constant time transformation at bytecode level and constant time preservation at machine code level. So by composing all these components, we eliminate all the execution variabilities of secret in V8. So far I mentioned transformation so many times, but what does constant time transformation really mean? The CT transformation requires two operations. First is control flow linearization. Another one is data flow linearization. The most important building block for control flow linearization is using bitwise AND and bitwise OR to select two values, X or E in this example, depending on a secret, without using branches, so that we can use this building block to merge two arbitrary execution paths into one. I have to skip how this bitwise trick works due to time limitation, but this is basically how C-movie instructions works at a source code level. Well, for data flow linearization, we can convert a single array access to accessing the entire array, then keeping the desired result, and use control flow linearization to remove the redundant branch. In Scooti, we eliminate the secret-dependent control flow in a similar way. We execute all the paths and keep the result from the desired path. However, unlike linearizing integers in cryptography libraries, we also need to handle arbitrary data types. So this brings us back to sorry for that. This brings us back to the technique challenge 2. Transformation must be able to handle arbitrary data types. For example, in a simple serverless function, one variable can be object, integer, string, noun, or undefined in different branches. So we extend the control flow linearization to enable linearization of accesses to references and objects. Here we have a key assumption that the metadata of the secret, like size and type, they are not secret. So for references, the linearization is just like linearizing integer. But for objects, the linearization will iterate through the entire object and merge each byte of them. After solving linearization for arbitrary data types, we also need to think about how to hide the access pattern for arbitrary data types. Here comes our challenge 3. In prior work, we convert a single array access to accessing the entire array. It becomes really inefficient in complex data types. So for example, if you have a try implementation of an auto-correction dictionary containing 1 million words, originally the runtime of a lookup is just all size of the word, and now it becomes all size of the try, and it's 1 million in this case. For now, our solution is still to simply access all the elements of an object. But in the future, we plan to revisit the obfuscation techniques like ORM to adopt it to provide a probabilistic guarantee, then reduce its runtime overhead. We currently have a partial implementation of CT transformer and CT interpreter. Now it supports 60 out of 176 V8 bytecode instructions, covering basic register, arithmetic, some comparison, and control flow operations. We manually verified 48 of them, have source code level secret-dependent instruction handler, and we also manually transformed one of it, the getKey property instruction handler, to be constant time. So now, when accessing an object property with a key, Scooti will access all the elements of the object. For evaluation, we currently have two micro benchmarks, select and indirect call. The select function takes a secret condition and a public value. It returns the public value or undefined, depending on the secret condition. The transform version converts it to a branchless selection. And the indirect call function takes a secret index and executes a function of the index in a function list. So this transformed version converts it to a for loop of function calls. We show the transformed version of the in source code, but the real transformation happened in bytecode and assembly level. We evaluate these two micro benchmarks with three configurations. First, the baseline setup, which execute non-constant time bytecode with non-constant time handler. And second, CT bytecode only setup, execute constant time bytecode with non-constant time handler. So the light gray bar here shows the additional overhead on top of baseline due to executing constant time bytecode. And third, the CT bytecode handler setup executes the CT bytecode and CT handler. The dark gray bar shows the additional overhead of executing CT handler. So for these two benchmarks, Scooti introduced 8% and 64% overhead respectively. It's worth mentioning that the overhead vary from programs and the size of the object a lot. In the future, we first plan to adopt ORM-style techniques into V8 memory management. And second, we plan to provide a composable formal proofs for the overall constant time execution. And we also plan to evaluate Scooti from both security and performance perspective in real-world applications. And last, we also want to consider the secret leakage during transient execution. In summary, here we present Scooti. It provides cache timing side channel mitigations for serverless applications. Scooti modifies V8 engine to support automatic constant time transformation for JavaScript applications. And our solution can be generalized to any other language runtimes. That concludes my talk, and I'm happy to take any questions.
Okay, we have time for questions. Yes, Katalin.
This is very ambitious work. So I have a few questions. One is, what do you think is an overhead that the kind of developers would be willing to accept in this space? Like you mentioned 60%, would that be something that you could imagine plausible or not?
No, for developers, to be honest, I guess they won't accept the overhead above 10 or 20. I guess that's probably the maximum overhead they would like to accept. But for this work, currently we don't have introduced any annotations for secrets or refined secrets. So for general applications, I think the performance highly depends on how the developers provide the annotations for the secret they really want to protect. So this will affect the performance a lot. And probably in the next step, we could provide a more fine-grained type system with different levels of privacy control for the developers to let them tune the performance and the privacy.
My second question, if I may, is with respect to proofs. Like you're applying this to like production V8 engine. Like, can one do proofs in that setting?
Yeah, that's a very good question because we do get stuck here a little bit because currently V8 is C++ implementation plus some DSL turbo and some assembler to construct their handler. So what we currently can do is just simply manually modify that, and this could be quite tricky, I would say. So ideally, I think we can use existing tools to extract part of the V8 implementation into at least it's a static type language, and we already have working on transforming the C++ code to custom code. So that's one way we can achieve that. So take part of V8 out and using existing to do custom transformation for them. And probably another way is to pick another tiny implementation of V8, JavaScript engine. Yeah.
I saw there was another question over there. In the meantime, Xavier, you can set up.
Hey, thank you for the nice talk. I really like the setting of the problem you address. I'm curious a bit about how feasible it is for an attacker to do the kind of attack you presented in a real-world setting where there are many serverless applications. How easy it would be to target a specific application or to get secrets? Is there any analysis on this, like a study or a benchmarking?
Sorry, just to confirm, is your question about how practice is the current, like the ability of the observatory? Yeah. So first, we do have practical attacks in noiseless environment in cloud. That is, I guess, 2015. Showed the last level cache side channel is practical. Though for noisy environment, currently, I guess a lot of researchers are working on that, but technically, in practice, it's not very feasible. However, I think from security perspective, we would like to have a solution even for theoretical attack. We don't want to be just find this is really practical, but we don't yet have a solution. So, yeah.
Thank you.
Okay, then let's thank Yayu again.